Imagine standing inside a quiet manufacturing cell. A six-axis robot repeats the same movement over and over again with extraordinary precision. Now, um, stop watching the robot. Watch the operator. That's where today's conversation begins.
Yeah, it really is a profound shift in perspective when you actually do that, when you kind of force yourself to look away from the motion of the machine and just, look at the stillness of the person standing right there.
Right. And welcome to the deep dive. Today, we are not doing a standard technology review. We aren't looking at the latest artificial intelligence release notes, and we definitely aren't speculating about some science fiction future.
No, we're doing a deep dive into engineering judgment.
Exactly. On the table today, we have this really fascinating stack of sources. I mean, we've got field notes from industrial automation engineers, maintenance logs, essays from industrial designers, and some really detailed case studies straight from the manufacturing floor.
And the missions for this deep dive is to basically synthesize all of this into a single, cohesive understanding of where human capability actually fits into an increasingly automated world.
Because of the central thesis that emerges from all these documents, it's actually quite clear that it really challenges how we typically talk about technology.
Yeah, the thesis is essentially this: robots execute, humans judge, and engineering succeeds when both of those are designed to complement one another rather than, compete.
Which sounds incredibly elegant, but I want to make sure this is actually useful for you, the listener. Because whether you are a mechanical engineer designing these systems, or an operations leader trying to integrate them, or just a curious professional trying to figure out what the future of work actually looks like, this conversation is going to change how you view the relationship between human expertise and automation.
I really believe it will, because we're using industrial robotics as our primary lens today. But the underlying mechanics of this relationship, they apply to almost every field where a human being works alongside a highly capable system.
So let's just start with what happens the moment someone walks onto a factory floor. I mean, I've done it. You stand there on the concrete under those really bright halogen lights, and you're listening to the high-pitched whine of the servo motors.
And the sharp hiss of the pneumatics, right?
Yeah, exactly. And you watch this massive steel arm whip around, stopping within fractions of a millimeter of its target just over and over again. It is incredibly easy to get entirely captivated by the machine.
Oh, it's totally hypnotic. And, human beings are highly visual creatures. We are naturally drawn to motion, especially motion that mimics something we already understand, like a human arm reaching, grasping, and moving an object.
And that visual mimicry, it leads directly to the most common assumption people make. Whenever automation enters the public conversation, the narrative just immediately collapses into a single question.
Right, the classic, will robots replace people?
Exactly. But our sources argue that this is actually the least interesting question we could possibly be asking.
It is an understandable question, for sure, but it's fundamentally flawed because it relies on this false equivalency.
How so?
Well, when we watch a robotic arm perfectly mimic a human motion, like lifting a heavy steel casting, for instance, we just naturally assume that the motion itself was the human's expertise. We equate repetition with value.
Okay, let me stop you right there because I actually want to challenge that a bit based on the sources. From a purely economic standpoint, if an operator used to move, say, 100 parts an hour, and now a robot moves 300 parts an hour, the human has been replaced in that specific function, right?
Physically, yes.
So how is asking about replacement a flawed question if the replacement is visibly, physically happening?
Because it completely misidentifies what is actually being replaced. The physical presence of a person doing a repetitive task is being replaced, absolutely. But the engineering reality, and this is where the conversation really turns, asks a much deeper question.
Which is?
What work should never have required human judgment in the first place?
Wow. Okay. I've really never considered that distinction before because we almost always frame automation purely as a productivity metric, We look at dashboards and ask about throughput, cycle times, yield.
Yeah, and those are secondary benefits. But if you look closely at the field notes regarding the initial deployment of industrial robotics in heavy manufacturing, the primary driver wasn't actually just speed.
It was something else.
Yeah, it was a removal of the human body from environments that are fundamentally hostile to human biology.
Right. Okay, that makes a lot of sense. The sources talk about tasks that are perfectly suited for automation, and honestly, they aren't glamorous at all.
Not even a little bit.
We're talking about lifting 40-pound brake rotors 2,000 times a shift, or reaching into a chemical bath, standing in a room filled with aerosolized paint, or just breathing in toxic fumes all day.
Just think about the biological toll of lifting 40 pounds, twisting your spine, placing it down, every single minute, 8 hours a day, for 20 years.
It's devastating to the body.
Exactly. The human spine is simply not engineered for that kind of repetitive stress cycle, but a steel machine frame is. So when we look at that and ask, did the robot replace the person? We are missing the entire point.
The robot replaced the musculoskeletal degradation.
Exactly. The robot replaced the chemical exposure.
So it's essentially an exposure reduction measure. When you frame it like that, it feels much less like this sci-fi competition between humanity and technology, and much more like a necessary correction of past industrial practices.
Precisely. And this brings us to a really specific case study in our sources that perfectly illustrates this dynamic. It involves a robotic system designed specifically for handling explosive components.
I really want to dig deeply into this one because on the surface, if someone walks into a facility and sees a highly sophisticated robotic arm delicately moving high explosive materials, the immediate assumption by any outside observer is going to be, oh, they automated this to cut labor costs, or a machine is cheaper than a human operator.
Which completely ignores the actual reality of handling explosives. Let's just walk through what a manual operation in that environment actually looks like for a human being.
Okay, paint the picture.
So, an operator standing in a blast-proof room, they're wearing incredibly heavy personal protective equipment. They have to maintain intense, completely unbroken concentration.
Because if they don't...
Right, because they're physically moving materials that, if dropped or struck with even slightly too much force, could end their life instantly.
The psychological weight of that just has to be staggering. I mean, it's not just the physical movement. It's the adrenaline, the stress, the constant low-level awareness of the consequences of a single physical slip.
It is an immense cognitive load. It wears you down. Now, when the engineering team introduced the robot to handle the physical transfer of those explosive components, they weren't trying to eliminate the operator's expertise from the facility at all.
Because the operator is the one who actually understands the properties of the explosives, right?
Exactly. They understand the environmental conditions required, the subtle visual cues of a degraded component. The robot doesn't know any of that.
So they took the physical danger and just handed it to a machine. There is this profound human element noted in the text that really struck me here. The author points out that if you send a robot into that blast room, the robot doesn't complain about the risk.
No, it doesn't.
But far more importantly, neither does the operator's family.
That is the absolute core of it. We're talking about an operator who now gets to go home safely at the end of every single shift, without exception, because a machine took on the physical risk of the actual handling.
But I do want to push back on the operational side of this just a bit. If the operator is no longer in the room physically handling the material, don't they kind of lose their edge? Like, don't they lose that tactile connection to the work that made them an expert in the first place?
That is a very real concern in automation design. Absolutely. It's often called out-of-the-loop syndrome. But look at how this specific system was structured in the case study.
Right. They didn't just send the operator home.
No, the operator didn't leave the process at all. They were just relocated outside the blast zone. They were positioned at a control station with high-definition visual feeds and comprehensive environmental telemetry.
So the dynamic just shifted.
Exactly. The robot became the safest pair of hands in the room, but the operator remained the most important mind.
Safest hands, most important mind. I love that. So the operator is still actively engaged in the process. They just aren't the ones risking their fingers or their life to do it.
Precisely. They are making all the critical decisions, like, is the material behaving as expected? Are the environmental controls totally stable? Should we pause the run because a lot of raw material looks slightly inconsistent today?
And their judgment is now completely unclouded by personal physical fear?
Yes. When you remove the stress of potential death from a human being, their capacity to make clear analytical decisions actually increases dramatically.
That really reframes the entire goal of industrial design for me. I mean, good engineering rarely asks, how can we remove people from this facility? Instead, it looks at the workflow and asks, where are people adding the least intellectual value while simultaneously accepting the greatest physical risk?
That is a massive shift in how we evaluate the deployment of technology. The goal in the explosives case study was never about replacing the human's expertise. It was about creating the actual conditions where that expertise could be applied safely for a much longer career without the degradation of stress and danger.
To truly understand why this partnership between the operator and the machine actually functions on a practical level, we really need to break down the mechanics. We need to look at first principles.
Right, because they operate in completely different ways.
Exactly. The sources draw a very sharp line between the intelligence of the machine and the intelligence of the human. So let's deconstruct that. Let's look at the anatomy of execution versus the anatomy of judgment.
Let's start with the machine, the anatomy of execution. When we talk about a six-axis industrial robot, we need to understand what it actually is at its core. It is essentially a series of mathematical coordinate frames brought to life by motors and encoders.
Right. And for you listening, if you might not be super deep into robotics, how does the robot actually know where it is in space? Because, I mean, it doesn't have eyes in the human sense.
No, it relies on closed-loop feedback. Inside every single joint of that robot arm is a high-resolution encoder. As the motor turns, the encoder counts pulses, sometimes hundreds of thousands of pulses per single revolution.
Oh, wow. That is incredibly precise.
It is. The robot's controller knows exactly how many pulses correspond to a specific angle of that joint. It calculates the position of all 6 joints simultaneously to place the tool tip exactly where the programmer told it to go, down to a tiny fraction of a millimeter.
So it's fundamentally just geometry and math. It is executing a script, like move joint 1 to this angle, move joint 2 to this angle at this specific speed.
Exactly. And because it is purely mathematical execution, it possesses a trait that human beings simply do not have: perfect constraint.
Perfect constraint, meaning it just does what it's told no matter what.
Right. If you give a robot a well-defined objective, it will perform it with a consistency that, frankly, borders on the miraculous. It doesn't get distracted by a loud noise on the other side of the factory. It doesn't get tired at the end of a really long 12-hour shift.
And crucially, it doesn't improvise. The sources make a really big point about this.
Yes, the absolute lack of imagination. A robot will never be halfway through a highly complex welding cycle and suddenly think, you know, I bet if I just cut across this corner right here, I could save 2 seconds to get this done faster.
Which, to a human, honestly feels like a limitation. Like, we pride ourselves on finding efficiencies, on life hacks, on figuring out a faster way to do literally anything.
Sure, but in an industrial environment, human improvisation is incredibly dangerous. The inability to improvise means the inability to deviate from a known, tested, mathematically verified safe parameter.
Because the stakes are so high.
Exactly. When you are swinging a 200-pound piece of metal through the air, you do not want the system holding it to suddenly get creative. Execution is entirely about constraint and repeatability.
That makes perfect sense. The robot's superpower is its rigidity. But then we look at the other side of the equation. Let's look at the anatomy of judgment, which belongs exclusively to the human operator standing outside that robot cell.
And this is where things become much more difficult to quantify. We talked earlier about the operator just observing the machine. What they're actually doing in that moment is relying on tacit knowledge.
Tacit knowledge. Let's really unpack that, because it's a term that gets thrown around a lot in like knowledge management and corporate seminars, but how does it actually apply on a gritty factory floor?
Well, tacit knowledge is basically the knowledge you possess that you cannot easily articulate or write down in a manual. Think about riding a bicycle. You can't just hand someone a complex physics equation about angular momentum and expect them to immediately know how to balance on 2 wheels.
Right, they have to physically feel it.
Exactly, they have to experience it. So how does that look for a machine operator? It looks like an operator listening to the ambient noise of a massive stamping press.
They aren't looking at a decibel meter or a chart.
No, but they have stood next to that specific press for 5 years. They know the exact rhythm, the exact pitch of the metal shearing. And then one Tuesday, they hear a sound that wasn't there on Monday.
Just a tiny variation.
Yeah, a slightly sharper crack or maybe a slightly longer groan from the hydraulics.
And no sensor on the machine has tripped. No dashboard is flashing red.
Because the programmers never thought to install a sensor to measure that specific acoustic profile. The operator is noticing a pattern that nobody ever thought to write into a measurement program.
Or maybe they pick up a finished component and realize the surface finish just feels, I don't know, slightly more abrasive than usual.
Exactly. They are integrating thousands of unprogrammed sensory inputs simultaneously. They are processing ambient temperature, humidity, sound, vibration, visual anomalies, and they're comparing it instantly against years of historical experience.
They are answering a question the robot doesn't even know exists.
Beautifully said.
Yes. I was trying to come up with an analogy for this while I was reading the field notes, and I kept coming back to driving. It's the difference between following a GPS perfectly, that's the robot, and knowing not to drive down a road because you can physically see it's flooded.
That is an excellent way to frame it.
Right. Think about it. The GPS is the execution engine. It has a mathematical model of the map, and it calculates the most efficient route. It tells you to turn left in 400 feet. It executes its code flawlessly.
But it doesn't see the real world.
Exactly. If there is a water main break and the road is under 3 feet of water, the GPS doesn't know. The screen just says the route is perfectly clear.
Because the mathematical code no longer matches the physical reality.
Right. And if you are relying purely on execution, you drive your car straight into the floodwaters. Judgment is what recognizes when reality has quietly stopped following the instructions. You look through the windshield, you see the water, and you override the system.
You provide the necessary bridge between the model and reality. The GPS knows the rules of the road, but you understand the context of the environment. One of the essays in our stack actually captures this industrial dynamic beautifully.
What does it say?
It states that a robot is built to answer one question. Did the program sequence complete?
Like, did it reach coordinate XYZ without the motor drawing too much current? Yes or no?
Exactly. But an experienced engineer or an experienced operator asks a fundamentally different question. Why did the system behave differently today?
The machine knows what happened. The human wonders why it happened.
And this leads us to a fascinating paradox that appears in almost every successful automation project detailed in these logs. There is this common assumption in management that if you automate a process, you completely remove the uncertainty from that process.
I have to admit that was kind of my assumption too. Like, if I bring in a perfectly calibrated, mathematically precise machine, the operation should become perfectly predictable, right? If it does the exact same thing every time, where's the uncertainty even coming from?
That is the illusion of automation. Automation doesn't remove uncertainty, it simply relocates it.
Okay, I need you to walk me through this one. How does a perfect machine create relocated uncertainty?
Let's use a very specific manufacturing scenario from the sources. Imagine we have a high-speed production line manufacturing precision medical devices.
How?
We introduce a highly advanced vision system to inspect the parts as they come off the line.
A vision system, so like an industrial camera hooked up to an image processing computer.
Yes. And it is incredibly capable. It is checking dimensional tolerances down to the micron level. It can measure the radius of a curve faster than the human eye can even register the part moving past.
Incredible execution.
Right. Now, for 3 months, production is perfectly stable. The vision system passes millions of parts. The repetitive work is, as you said earlier, perfectly predictable.
The variables of the repetitive work are locked down.
But the physical world is never truly static. Suddenly, on a random Thursday afternoon, the vision system detects a dimensional deviation. The part is out of spec by 3 microns.
So it catches an error.
Yes. The system instantly sends a signal to a programmable logic controller, and the line just stops. The machine did its job perfectly. It executed. It knows exactly what happened. A measurement fell outside the program's threshold.
But the machine has zero curiosity about the context.
None whatsoever. It doesn't care. It just stops. This is where the uncertainty has been relocated to. The human operator now has to look at that stop line and navigate a vast sea of uncertainty.
Because they have to figure out the why.
Exactly. Why did that specific deviation suddenly appear today after 90 days of flawless production?
Because the system can't tell them why. It just says error code 404, dimension out of tolerance.
Right. Now the human judgment has to take over. The operator has to ask all the questions the machine cannot. Did the ambient humidity in the factory change overnight, causing the material to swell slightly?
Oh, that's a good one.
Is there a microscopic wear pattern developing on a cutting tool 3 stations upstream? Did the supplier of the raw plastic resin change their chemical composition slightly, altering how it flows into the mold?
So the machine reduced the uncertainty of the measurement, but it basically highlighted the uncertainty of the environment.
Yes. As you lock down the variables of the repetitive work, the remaining work, the anomalies, the edge cases, the slight drifts in physical reality, becomes heavily dependent on human judgment. As the machine gets better at execution, human judgment actually becomes more valuable, not less.
Because reality always has a head start on the dashboard.
Oh, that is a critical concept right there. Say more about that.
Well, think about the timeline of an error. By the time a warning light actually flashes red on a control screen, the physical reality of the process has already degraded. The dashboard is essentially a lagging indicator.
It only reports what has already failed.
Exactly. An experienced technician has probably already sensed that the machine was struggling long before that. They might have felt a slight vibration in the floor grates an hour before the sensor finally crossed its mathematical threshold to actually trigger the alarm.
Because the machine's sensors are strictly limited to what the original programmers told them to care about. They are looking at the world through a tiny straw. But human sensory input is vastly broader and completely unstructured. We take in the entire context of the room simultaneously.
Which brings up a really interesting behavioral observation noted in the design essays. When you watch these machines interact with complex physical environments, you actually start to notice a personality trait.
Now, you have to be careful here. Anthropomorphizing industrial equipment can lead to a lot of bad assumptions.
I know. But the author of one of the essays describes it as a quiet humility. And I honestly think it's a brilliant way to conceptualize their limitations. Industrial robots possess a trait that human beings, particularly in corporate environments, occasionally struggle with.
Which is
They are remarkably honest.
honest in the sense that they entirely lack the capacity for deception.
Exactly. A robot never pretends to understand something that exists outside of its design parameters. It never invents confidence just to save face. It never mistakes its ability to repeat a task for actual comprehension of why the task even matters.
If a robot encounters a situation it doesn't know how to handle, it does one thing, and one thing only, it simply stops.
It stops and waits. And the author contrasts this with human behavior in a corporate setting, which I found hilarious and painfully true. Like, humans occasionally announce false confidence in a project review meeting when they have absolutely no idea what they're talking about.
Oh, all the time. Or they will write a 30-slide PowerPoint presentation with complex charts to obscure the fact that they don't actually know why a system failure occurred. We are narrative creatures. We try to fill the gaps in our knowledge with stories, with speculation, with plausible-sounding explanations.
We bluff.
We bluff. The robot never bluffs. It just stops, shuts down its drives, and waits for reality to make sense again.
There is a specific visual described in the field notes that illustrates this dynamic perfectly. I want you to picture this. Imagine you are watching that highly complex, beautifully engineered robot performing its cycles. It's moving fast, grabbing parts, assembling them.
Okay, I'm picturing it.
Suddenly, it just pauses. It doesn't break down. It doesn't crash into a wall. It just stops midair and waits patiently.
Then why did it stop in this scenario?
Because a tiny 8mm steel locating pin on the workbench has rolled slightly out of position. It's maybe half an inch away from where it should be.
Let's analyze why the robot stops there. Because from the outside, it looks trivial, right? Why can't the robot just reach half an inch to the left and grab the pin?
Because it doesn't know what left is.
Exactly. Unless it is equipped with a highly adaptive 3D vision system, which adds massive layers of complexity and latency, it is moving blind to a coordinate in space. It expects the pin to be a coordinate XYZ. It closes its gripper. Its internal sensors register that the gripper closed completely without encountering the physical resistance of the metal pin.
So a logic gate triggers.
Yeah.
Expected state, gripper open 8mm. Actual state, gripper fully closed. Error.
Yes. The robot doesn't guess where the pin went. It doesn't start squeaking the table trying to find it. It doesn't try to improvise a new assembly method without the pin. It just stops.
And then the human operator quietly walks over. They assess the situation at a glance. They see the pin rolled away. They pick it up, gently place it back into the fixture. Maybe they tighten a loose set screw to stop a faint metallic vibration that caused the pin to roll in the first place.
They fix the root cause.
Right. They step back, hit the reset button, and the robot immediately resumes its cycle.
It's almost as if the machine was just politely waiting for the human to notice the anomaly.
The robot handles the geometry. The human handles the anomaly.
That division of labor is where true efficiency actually lies. The machine was perfectly patient because it lacked the context to resolve the discrepancy. The humor in that situation, watching a $1 million machine defeated by a rolling pin, comes from recognizing its total honesty. It didn't know, so it did nothing. It relied entirely on the human to restore order to its universe.
That visual fundamentally changed how I view the whole dynamic of automation. We spent so much time worrying that robots are our replacements. The narrative is always man versus machine, but when you watch them interact with an experienced operator on a factory floor, they don't look like replacements. They look like deeply dependent tools.
Because they require highly structured environments to function. And the physical world naturally tends toward entropy. Things wear out, things shift, temperatures change.
They need us to manage the chaos of reality so they can perform the miracle of consistency.
Which brings us to the highest philosophical peak of this discussion, I think. We have to look at the concept of restorative engineering.
Restorative engineering. This is the core of the episode's focus. If the true purpose of engineering is not replacing human capability, what is it?
The documents we are reviewing argue that technology reaches its highest value when it protects and restores human capability.
Restoring people rather than replacing them. Let's really dig into what that actually means in practice, because restoring people sounds a bit abstract.
It means engineering systems that remove the cognitive and physical overload of mundane repetition. When you force a human being to act like a machine, to do the exact same physical motion or the exact same data entry task thousands of times, you are underutilizing their brain and overutilizing their body.
You are basically wasting their capacity for judgment.
Yes. Good engineering gives people fewer reasons to stand in harm's way and fewer reasons to turn off their brains. And by doing so, it creates more opportunities for them to apply their experience where experience actually matters.
At the edges of the process.
Exactly.
If you look back at the history of technological advancement, very few meaningful engineering advances have actually eliminated the need for human judgment. Like, we introduce more software, we introduce advanced AI, we deploy fleets of autonomous robots in warehouses. The systems become vastly more capable.
But they also become vastly more complex.
Right. And here is the counterintuitive part. Complexity rewards human judgment.
Why? Because complexity creates unpredictable edge cases. The more variables you introduce into a system, the more interactions you have between those variables. You create moments where reality quietly drifts away from the assumptions built into the software model.
I think about aviation here. The autopilot on a modern commercial jet is an incredible piece of automation. It can fly the plane from takeoff to landing in perfect conditions. But when a flock of birds strikes the engines at 3,000 feet, the complexity of the failure requires the pilots to instantly take manual control, assess a cascading series of alarms, look out the window, and judge where to put the plane down.
Because the system executed perfectly until it couldn't. Then judgment had to take over immediately. When a system is highly complex, the ability to recognize that reality has drifted from the model is the most valuable skill in the room.
So it's an engineering problem.
It is an engineering problem, not just a software problem, to design systems that allow humans to actually retain that situational awareness.
Right. You don't want the humans so disconnected from the process that they don't even know what to look for when the alarm finally rings.
Exactly. You want them engaged in the flow of the work, managing the parameters, observing the trends, applying their tacit knowledge to keep the system optimized. Look at autonomous mining, for example.
Oh, that's a great example from the sources.
Right. The autonomous trucks handle the repetitive, driving the execution. But the human operators in the control center are the ones constantly judging the shifting terrain, the weather conditions, the overall choreography of the fleet. The execution is offloaded, but the judgment is amplified.
This is where I want to connect this directly back to you, the listener. Whether you are working on a factory floor or in a corporate office or designing software, think about your own industry. Think about the technological shifts you've personally navigated over the last 5 or 10 years. When a new software platform or a new AI tool or a piece of physical automation was introduced into your workflow, what actually happened?
The repetitive busy work likely disappeared. The manual data entry, the rote calculation, the heavy lifting.
But ask yourself, what part of your job became more valuable after that automation was introduced?
It is almost always the interpretive work. When the busy work disappears, judgment is the only thing left. Your ability to interpret the data, to question the output of the AI, to notice the subtle anomalies that the software glosses over because they don't fit the expected pattern, that becomes your primary contribution.
The goal of automation was never to stop asking experienced people to do their jobs. The goal was to stop asking experienced people to spend their days doing work that experience was never needed for in the first place.
We really have to stop viewing the highest ambition of automation as replacement. Replacement is an incredibly shallow metric. It looks good on a short-term financial spreadsheet, sure, but it completely hollows out the institutional knowledge of the organization.
Restoration is a much higher ambition, creating conditions where human experience matters more, not less. Designing tools that act as the safest pair of hands so the human can remain the most important mind.
It makes you wonder how much human potential is currently buried under repetitive tasks that machines should have taken over years ago.
That is a staggering thought. How many subtle process improvements are we missing right now? How many critical errors are we failing to notice early because our mental bandwidth is entirely consumed by just keeping the machine fed or typing data into a rigid interface?
That is the core tragedy of poorly designed automation. If a system does not free the human mind to judge, interpret, and innovate, it has fundamentally failed as an engineering project, no matter how much faster it claims to be.
This has been a profound shift in perspective for me. We started this hour by simply standing on a factory floor, watching a robotic arm perform a flawless, repetitive cycle. And we've ended up looking at the fundamental nature of what human expertise actually is.
It forces us to define what we bring to the table that a machine simply cannot.
Perhaps the real lesson isn't that robots will replace judgment. Perhaps it's that every successful automation project reminds us just how valuable judgment has always been.
Reality always gets the final vote. Good engineering simply learns to listen earlier.
Think about your own daily workflow this week. What robotic, repetitive tasks are you clinging to that are burying your own human judgment? If you could offload the execution, what anomalies might you finally have the bandwidth to notice? Give yourself the opportunity to stop being the machine so you can go back to being the mind.